Hello everyone, hope you're doing well. In this video, we'll look into the next concepts of rotational motion, and those are rolling. We'll try to understand what do we mean by rolling. Then we'll see what is the minimum friction required for rolling, and then we'll see kinetic energy of rolling bodies. To start with, let's try to understand what do we mean by rolling or rolling motion. A body with both translation and rotational motion is called rolling motion. So if a body is having both rotational as well as translational motion, then that particular motion is termed as rolling motion. Like if you look at a vehicle moving, the tire of the vehicle is rotating as well as moving forward. In fact, that rotational motion of the tire is converted into the linear motion on the road. So the tire, we can say that the tire is rolling on the ground. Now let's look at various things that are related to rolling. And this figure, if this is rolling, let's say this is the velocity of the center of mass. This is the velocity with which it is moving. Now if it completes one rotation, then what is the distance covered? Distance covered would be equal to 2 pi r. I'll say 2 pi r is the linear distance covered, right? And what is angle covered? Angle covered is 2 pi. So we have linear distance covered. I can write if linear distance covered is s, then s equal to r theta. This is the relation between the linear distance covered and the angular displacement of a rolling body. So if I differentiate both sides, what would I get? ds by dt would be equal to r into d theta by dt. So we'll get v equal to r omega. So velocity of the center of mass of the body, or velocity, linear velocity of the body, is radius times the angular velocity of the body. Now when this condition is satisfied, we say that the body is in pure rolling. That is, the total rotational motion is converted into linear motion, right? Now we have other conditions also. If v is less than r omega, that means what? The body is having greater angular velocity but lower translational velocity. Then this situation is called slipping. You can visualize this situation to be a situation where a vehicle is stuck in mud. We are accelerating, the tire is rotating, but the vehicle is not able to move forward at the same rate. So when velocity is less than r omega, or the translational motion is less than the rotational motion, then we say it is slipping. Now the other condition that we can have is when v is greater than r omega, that is translational motion is greater than rotational motion, then we say it is skidding. Then what happens is we say it is skidding, right? So skidding, this you can visualize again. Let's say you're moving in a vehicle and you apply brakes, then you'll see that the rotational motion is less than the translational motion. As a result of that, the vehicle skids. So in general, what I can write, I can say in case of rolling motion, v equal to r omega. So mostly we have only pure rolling in our syllabus. So this is the definitions that we're required to know. Now if I generalize this one for acceleration, if I further differentiate it, I'll get dv by dt equal to r into d omega by dt. So I can say dv by dt is linear acceleration equal to r into alpha angular acceleration. So these are the two conditions that I can use for pure rolling. V equal to r omega and a equal to r alpha. Now after that, let's look at the minimum friction required for a body to undergo pure rolling. So here what I'll do is I'll just take some body and I'll apply a force. Let's say I've taken a cylinder as an example, and then we'll generalize it for any body. Let's say I apply a force F on the top of the body. Now let's assume that friction is acting in backward direction. It's not necessary that the friction should act in the backward direction. It can act in forward direction also. If the value of friction, final value of friction, I get positive, then my assumption or our assumption is correct. And if the final value of friction that we get is negative, that means the friction is acting in opposite direction. Now let's say this is moving with an acceleration a in the forward direction. Then by writing equations for linear motion, I can say ma equal to how much? Applied force minus frictional force. Now after that, let's write equation for rotational motion. If I write equation for rotational motion, what will I get? I will get Fr plus Fr, torque, net torque equal to I into alpha. So from this, what I can write? I can write F plus F into R equal to how much? I alpha. Or I can write F plus F. Capital F is force and small f is friction equal to I is, I'll write this, if I take it as a cylinder, I is how much? Mr square by 2. Alpha is A by R and 1 R from this. So if I cancel all R's, I'll be left with F plus F equal to MA by 2. Now we have equation 1 and equation 2. If I want to find friction, so I have MA equal to F minus F. So I can write 2 into F plus F equal to how much? MA. And instead of MA, I can write F minus F. So from this, what I can get? I will get F equal to, in fact, F equal to, I'll get minus 3F, or F equal to frictional force equal to how much? Minus F by 3. In this particular case, the minimum friction required for the pure rolling is how much? Minus F by 3. Now, what all factors this minimum friction required depends on? It depends on the point where the force is applied, right? And of course, the shape and size of the body, or the nature of the body, or in terms of that, we can say the moment of inertia of the body. So if I want to generalize this what we have done it for a solid cylinder. Now let's say generally I'll apply the force at a distance x from the top and the moment of inertia is only L. In that case, what will happen? I'll get, as usual, MA equal to how much? F minus F, and torque in that case will become Fx plus F into R equal to I into alpha. Alpha, I'll directly write it as A by R. So from this, I want to find what is friction. So if I want to find friction, I have to eliminate A. So here A can be written as F minus F by M. So I can write F into X plus F into R equal to I by R into F minus F by M. So solving this, what we get? We'll get F into X plus F into R equal to IF by MR minus IF by MR. So I'll take all the terms of F to one side and the other terms to other side. So in that case, what will I get? I'll get F of X minus I by MR into F equal to, we have minus F into R plus I by MR. This is what we got. So if I want F, what I can write, this can be further written as F into, I'll take out the negative sign. So this becomes MR, I by MR. So I can write it as MR into, so MR into X minus I. Is that okay? Minus I by MR equal to, of course we don't have minus F here, equal to minus F into MR square plus I by MR. So I can cancel this MR and MR. Now what am I left with? I am left with F equal to friction, minimum friction required would be equal to applied force into I minus M into R into X by I plus MR square. This is the minimum friction required for a body when the force is, for a body of moment of inertia I, when a force is applied at a height x above the axis, about the center of mass. So in this way we can find what is the minimum friction required. Again, there is one particular case where the object can rotate even without friction. That is, put F equal to 0, then you will get I minus MRX equal to 0. or x would be, so at x equal to I by mr, what will happen? The body can rotate without friction also. So hope you could follow this. So this is the minimum friction required for a body rolling on horizontal ground. Now let's look at a situation of body rolling down an inclined plane. So again, I'll assume this to be some body of moment of inertia I. An inclined plane, what is the force acting? Mg sine theta is acting downwards, and let's assume that friction is acting upwards. Now writing equation for linear motion, I can write Ma equal to how much? Mg sine theta minus frictional force. Now writing equation for torque, F into R, friction into R, equal to I alpha. I is, I'll write it as I alpha, I'll directly write it as A by R because we're assuming that it is under pure rolling. So from this, what will I get? I'll get F equal to IA by R square. Putting this in the first equation, I'll get MA equal to mg sine theta minus IA by R square. So A would be equal to how much from this? A can be written as mg sine theta by m plus I by R square. This is the acceleration with which the body would be coming down. And substituting this acceleration in this equation, I can find what is the minimum friction required. And if I want to find coefficient, minimum coefficient of friction, what is N? N would be acting in this direction, normal reaction. So I have F equal to mu into N. So F equal to how much? Mu into N is mg cos theta. By using this, I can find what is the minimum friction required also. Now let's look at the kinetic energy of rolling bodies. Now because a rolling body has both translational and rotational motion, it has both kinetic energy of translation as well as kinetic energy of rotation. So I can say, as it is written here, kinetic energy of rolling body equal to how much? Kinetic energy of rotation plus kinetic energy of translation. Now kinetic energy of rotation is given by half I omega square. This is half I omega square. And kinetic energy of translation is given by half mv square. So the total kinetic energy is equal to how much? Sum of both of them. That is half I omega square plus half mv square. Now here I can convert, so I can use V equal to R omega. So I can convert them, the total kinetic energy, into whatever it's like if, in terms of omega or in terms of velocity. Let's take an example. Let's say I take a ring. For a ring, I equal to how much? Mr square. Now I want to find total kinetic energy in terms of velocity. So what is kinetic energy total? Half I. Instead of I, I'll write mr square. Omega is V by R, so omega square can be written as V square by R square plus kinetic energy of translation, that is half mv square. So here this cancels, so I'll be left with what? Half mv square plus half mv square. So the total kinetic energy is equal to mv square. So a body rolling with velocity v would have greater kinetic energy than a body sliding or skidding with velocity v. That's because we have kinetic energy of rotation as well as kinetic energy of translation involved. Now let's look at the energy conversion that is taking place when a body rolls down an inclined plane. Let me assume that this is a hollow sphere, this is rolling down an inclined plane of height h. I need to find what is the speed with which it reaches the bottom, right? Now what is the total potential energy if initially it is at rest? Initial potential energy is mgh. Now what is kinetic energy when it reaches the bottom? It is half I omega square plus half mv square. Now I for hollow sphere is 2 by 3 mr square. And omega we know for pure rolling is V by R. So that would imply kinetic energy equal to how much? Half into 2 by 3 mr square into V square by R square plus half mv square. So that would be equal to 2 cancels. We have mv square by 3 plus mv square by 2. That is 5 mv square by 6. Now this is equal to potential energy mgh. From this, what do we get? V square equal to 6gh by 5, or V would be equal to root 6gh by 5. So in this way, I can find what is the velocity with which the object would come down. So what all factors does the velocity depends on? It depends on the shape and size of the object as well. If you look at linear translation, we say half mv square equal to mgh. There we are not bothered about the shape and size of the object. We only are bothered about the height. But here, the shape and size of the object also matter. So that is what is there in rolling motion. So what all things we have seen? We have seen what is rolling motion. Then we have tried to understand the conditions for, let's say, pure rolling. And as we have seen that only most of the questions that we get are based on pure rolling. Then we have seen what is the minimum friction required for pure rolling on horizontal surface. Then we went on to explain how does rolling come into picture in case of a body rolling down an inclined plane, what is its acceleration, friction and coefficient of friction. And after that, what we have seen is what is kinetic energy of rolling bodies and how the mechanical energy gets converted from one form to other form during the motion of or during the rolling of a body from a height. Hope you could follow this. Thank you very much and keep watching Get My Class videos. Thank you very much.